All right, so we're going to work through constant pressure calorimetry, which is pretty much what we were just talking about, but I broke the video in half, okay? So constant pressure calorimetry is how we are going to determine the amount of energy that is needed or released in a chemical reaction. In our lab, we're going to use coffee cup calorimeters with water making up the primary solution. Okay, the primary part of the solution. Effectively, we're going to make the reaction happen inside the water. We're going to monitor the temperature of the reaction container. It is that temperature change that helps us determine how much energy has been exchanged. So now we're going to use the Q equals CS times M times delta T equation. And so that's kind of how this is going to play out. So now there are some assumptions that make this work for us. And so we see the temperature and the change of the reaction in the temperature change of the water. So an increase in the temperature means that the reaction is exothermic. So if the temperature goes up inside the calorimeter, that means that it was an exothermic reaction. If the temperature goes down, that means it's endothermic. Okay, and so that's how that plays out. Now, we assume that the entire solution has the same specific heat capacity of a water. Now, here we go. This is a huge assumption, and I want to spend just a little bit of time on this, okay? We assume that the whole solution has the specific heat capacity of water, though we know it can't, okay? So, but water is the primary solution, or the primary component making the solution up. And because that's the way it is, we're taking the liberty and we're just going to say that the water does it all. Okay? It's not true, it's an assumption, but it makes the math easier for us, and that's how we're going to get around it. But it's accurate enough for what we're doing. Okay? And so, but water does make up the majority of the solution. And remember that we use specific heat capacity of water. The CS of the water is 4.18 joules per gram degree K for dilute solutions. Okay. Now, the heat gained or lost by the solution, the Q of solution, is equal in magnitude but opposite in sign. Okay, so for the heat gained or lost by the reaction. So the Q of the reaction is equal to the Q of the solution equals negative Q of the reaction, okay? So heat capacity of the reaction equals the heat of the solution opposite in charge of the reaction, okay? So Q of solution is specific heat of solution times the grams of solution times the change in T. Well, that's going to equal the negative heat of the reaction, and that's how we're going to work through that. So let me show you exactly how that works and exactly what that means. Okay, so let's scroll up and get you guys some clean space so that we can work through this problem together. Okay, now we're going to do a bunch of these too. So this is something that you're going to have a very good understanding of fairly quickly. So just relax, okay? We'll get you there, I promise. All right, so here's our sample problem. And there we go. So a calorimetry experiment is done with 75 milliliters of 1.0 molar hydrochloric acid and 75 milliliters of 1.0 molar sodium hydroxide. The temperature increased from 21.0 to 27.46 degrees Celsius in the solution. Total volume, when we add them up, is going to be 150 milliliters. The density of the solution is 1.0 grams per milliliter, and the specific heat capacity for water is 4.18 joules per gram Kelvin. What is the enthalpy change for this reaction in kilojoules per mole? Okay, first thing we want to do is we need a chemical reaction. So hydrochloric acid plus sodium hydroxide makes NaCl and H2O. So this is a acid-base neutralization. Because we have an acid, we have a base, we make a salt, and we make water. And so we're going to use the calorimetry equation above. Let's convert our milliliters of solution to mass of solution. And so that's why we gave our density. Okay. So here we go. Let's convert volume to mass using density. So we have a total volume of 150 milliliters. So we have 75 milliliters of HCl plus 75 milliliters of NaOH. Okay, so that equals 150 milliliters total. Okay, so now we have our 150 milliliters total. We are going to multiply that by 1.0 gram per milliliter. And so now 150 times 1 is 150 grams of solution. All right, so I'm going to just cheat and just write SOL''N. And this is equal to my M value. Okay, so we just found one. Now we got to find our change in temperature right here. Okay, so delta T is equal to T final minus T initial. Okay, so T final, we go up here, I can see that T final was 27.46 degrees Celsius minus 21.0 degrees Celsius. Okay, so my T final is going to be 6.46 degrees Celsius. Now, I'm going to do a willy-nilly substitution here. The magnitude of a degree Celsius, so remember, 1 degree Celsius, not on the temperature scale, but in magnitude, equals 1 degree Kelvin. And so I don't have to do anything. I can just say, oh, that's 6.46 K. Okay, because this is a magnitude. This is a subtraction between the two. And because we're subtracting those two values, I don't need to convert it. It's just K. Just do the math on it. If I wanted to convert it to Kelvin first, I could convert that to Kelvin, subtract that converted from Kelvin, and that would give me the same value as the 6.46 K. So there we go. Now we have our T final and we have our mass. So let's insert this into our equation. Okay, so our Q of our reaction is going to equal negative CS times M times delta T. Okay, so negative CS, negative 4.18 joules per gram K, times my mass, which is 150 grams. Put that over 1. We put the whole thing over 1 if it makes you happy, times my change in temperature, which is 6.46 K. You can put that over 1 too if you want. Grams, grams, K, K. This is going to leave behind a unit in joules. Yeah, we set it up right, so that's good, because heat should be measured in joules, or Q should be measured in joules or kilojoules. Okay, we do the math on it. I get 4,000 negative 4,050.4 joules. Okay, now I asked for this in kilojoules, as you can see in kilojoules. Okay, and so I'm going to convert this to kilojoules right away. To do that, I'm going to divide it by 1,000, so that's negative 4.05 kilojoules. Okay, now because we are at constant pressure, so we're doing this calorimetry at a constant pressure, we can say that we're all set to go. That means that our delta H is going to equal QP, and in this case that's negative 4.05 kilojoules. Okay, so we're still happy. We're good. We're at constant pressure, and so I can make this solution without any other alterations. So, all right, last thing we want to do is put this in terms of moles or molar quantities. So we're going to do this by saying, okay, well, molarity is moles per liter. Hopefully we remember that. And then we know that we have 0.075, so we have 0.075 liters of HCl. And we're going to multiply that by 1.0 big M. And what that does for me is that tells me that I have 0.075 moles of HCl. Okay, so my molar enthalpy is going to be my number of moles is the amount of energy released divided by the number of moles. So it's going to be negative 4.05 kilojoules divided by 0.075 0.750 moles. And that's going to be negative 54 kilojoules per mole. Okay, and so that's how we would do that step. Now this last step here, we may or may not do this from here down. That may or may not happen. But just so in case you're asked, there it is. So that is how we end up doing that. Okay. Now, again, if you have any questions, jot them in here so that you've got them so we know what's coming up. And we'll go from there. Now, we have one more thing. I'm just going to throw this on here quick because it's going to be pretty quick. And erase this. You can always pause and go back again if you need to, and that's all right, just so that you can see me. I don't even think I have any writing to do in this next one. So, okay, here we go. So, here we go. Constant volume calorimetry. This is called bomb calorimeter. Oh, I do have writing to do. I forgot. Okay, so if we're doing bomb calorimetry, what we're doing is we're doing combustion reactions inside a sealed container, which is done, so in a sealed container, which is submerged inside water in another sealed container. The temperature of this water is monitored, and we use that to calculate the amount of energy released in the reaction. Because this reaction is done in a bomb calorimeter, we have a constant volume. The heat transfer corresponds to the change in the internal energy rather than to the change in the enthalpy. So if we end up doing it, Q reaction is equal to the negative C of calorimeter times the change in temperature. Okay, and so C cal is the heat capacity of this calorimeter, and it's either going to be calculated or given. And so we'll see how we end up doing this in lab this year. I might just give you a value, or we might have to calculate one too. So we don't do much with bomb calorimetry because I don't have a bomb calorimeter. I'd like to, but I don't. So I'm just kind of throwing it out at you so you got it, you see it, and you know what's coming. So there you go. Talk to you soon.